Hello everyone, I am Harshavnath Tanti and I am your TA for this radio astronomy course. I am currently a research scholar pursuing my PhD under the supervision of Professor Avruth Datta, who is also the course instructor of this course. And welcome to your second week tutorial course. In this lecture, what we will do, we will study some sample questions on radiative transfer, which was not covered in the earlier lectures. So let's begin with reviewing what is radiative transfer. So if I define, there are four kind of radiative transfer. The first one being emission, where there is a media which is due to some reason it's emitting some radiation, and due to this emission the system is cooling down. Okay, now the second one is absorption, where a medium is absorbing all the electromagnetic radiation coming from the surrounding. The third one is thermodynamic equilibrium, means the amount of emission and absorption is same, so energy contained in the system is same. And the fourth one is LTE, local thermodynamic equilibrium, wherein in a macroscopic scale you will have thermodynamic you will have non-equilibrium, whereas in local scale, in smaller region, you will have thermodynamic equilibrium. Okay, so let us see our first example. So the first example is about when the temperature of a medium increases, the emission spectrum of the medium will shift to a higher energy or shorter wavelength radiation, shift to a lower energy or longer wavelength radiation, remain unchanged, as the temperature does not affect emission. So both shift higher and lower energy radiation. So I will give you a 10-second time, try to answer it, and after that we will proceed to what is the actual answer to this question. So the correct answer is A. The energy they shift to shift to higher energy, shorter wavelength radiation. See, if a system's temperature increases due to, and you have studied Planck's black body radiation. So due to Planck's law, what will happen? And since the temperature increased and it has a direct correlation with the intensity, so intensity will increase, and also that means the wavelength will also increase, decrease, because intensity has inverse relation with your wavelength. Okay, let's move forward to another sample question. That is, a radiative equilibrium in a planetary atmosphere occurs when the temperature remains constant throughout the atmosphere, energy absorbed by the atmosphere equals to energy emitted back into the space, conduction dominates over the radiation in heat transfer, the atmosphere is completely transparent to radiation. So your 10 seconds starts now. So the correct answer is B. The energy absorbed by the atmosphere is equals energy emitted back into the space. So the equilibrium in a planetary atmosphere will only happen if there is thermodynamic equilibrium maintained. Okay, this is TE. So if there is a medium here and emission both are same, then only the rate of emission and absorption is equal. Okay, and the temperature is maintained same. Now moving to another sample question. In a scenario where absorption significantly exceeds emission in a medium, the temperature of the medium will what? Decrease, increase, or remain constant, or there will be a periodic fluctuation. So So the correct answer to this question is option B. The energy will increase because if absorption increases, what will happen? The medium will the heat the temperature will rise. If the temperature will rise, how? Because it's absorbing all the energies from the photon, and this is also known as what? This is also known as radiative heating, a phenomena called radiative heating, where the absorption is significantly high. If you for an example, you go out in a sunny day, so what you will feel, you will feel more heat on your skin. That is because you are absorbing photons from the emitted by the sun. Okay, and also your environment is also getting heated up because of other phenomena. But there is also one reason that the your body is absorbing the IR radiations. Okay, so moving to another sample question. This is a NAT type question. So we will go through it. Means like it's quoting that there is a gas cloud which absorbs radiation at the rate of 5 into 10 to the power minus 9 watts per meter cube. If it is given the cloud's volume is 10 to the power 6 meter cube, and it's saying calculate the total energy absorbed in 1 hour. Okay, so here you can if you don't clearly remember, the way to answer is, the trick is to see the units. Okay, so watts per meter cube are, so you know what is that? Power is equals to energy over time. Okay, so energy is equals to what? Power into time. This is the hint to solve it. So the correct answer to this question is 18 watts. How? See, absorption rate is given per meter cube and you have the volume. So you just multiply by the volume, you will get the absorption means the power in watts. So power in watts will be what? 5 into 10 to the power minus 3 watts. And you have given 1 hour of time, and energy is calculated in what? Joules, which is in seconds. Means you have to multiply this 3600 with 5. So you will get 18 watts. Okay. Let's move on to another exciting problem. This problem says that there is a material with thickness 5 centimeter. Okay, there is a thickness of 5 centimeter, and it has an absorption coefficient of what? 60. It absorbs 60% of the radiation. Okay, 60% of the incident radiation. Okay, now intensity of the radiation is given. Okay, you have to find what is the linear absorption coefficient. Okay, so the trick is, here you have given the percentage of radiation absorbed and the thickness, and based on this you have to calculate the absorption coefficient. So the answer to this question will be 8000 per meter. Absorption coefficient of 8000 per meter. So by using the formula, the intensity absorbed will be what? Incident intensity into 1 minus the transmittance. Transmittance is what? 60% only. Okay, the incident intensity is what? Given in meter square. So 1 minus this, we will get what? We will get this quantity, and absorbed intensity is nothing but your mu into, you can say, thickness. You can, okay, so mu into thickness, you can, or in other terms, actually the formula will be divided by mu, and the mu will come here. Okay, so this, what you get is coming around to be 8000. Okay, now let's move on to the final question of the day. So we have to consider a medium here. with given a scattering coefficient and absorption coefficient. And there is also mentioned that there is an intensity which is incident of the on the median. Okay, it has a absorption coefficient and scattering coefficient. Now there is a wave coming, some of will scatter and some of will be absorbed. So, and the thickness given here is 20 centimeter. Okay, now what you have to calculate is the transmitted through the medium, means the radiation which is entering and transmitting through it. Okay, so the answer to this question will be be 36.79 watt per meter square. So using the transmission coefficient formula for we will have, which is this, we will have what tau is 0.05 into 20 centimeter. 0.05 per centimeter is what your optical, means tau is your optical depth, where s is the scattering coefficient. Okay, sigma is the scattering coefficient into this. Okay, and scattering, and this is the your absorption coefficient. Okay, now you calculate the tau on based on the optical depth, then calculate the optical depth, which is tau equal to 1, and from that you can calculate the intensity. Okay, so let's again revisit the values. Here it is mentioned that absorption coefficient is 0.5. Okay, so that's why the tau value here is 0.05 into 20 centimeter. Okay, so this is how the tau came to be. And tau, see, centimeter to the power minus 1 and centimeter, so dimensionless quantity. Okay, tau is coming out to be what? 1. Okay, so that's how you do it. So thank you.